Progress.
Hello, good morning.
Good morning.
Good morning.
Hi, Jana, Jordan. Could you guys do me a favor? I do need something from you, and that is I need to share screen. And okay, are you seeing the shared screen here?
Yes.
Okay, when you guys are going in, and I'm gonna get into the course in a second. I think both of you submitted the vaporization lab correctly. I'm just wondering how you did it because others are not.
I also I have Canvas on my phone, and on my phone it has a to do and assignments tab. So I said that it through the assignment, on the assignments, not through the modules.
You're not doing it through the, no, well, basically that's not the problem.
Oh, okay.
Oh crap, I'm in the wrong thing. Let's see. I have to get in the right course first. You guys doing okay?
Yeah.
Yeah.
Did you survive the test and its mistakes?
Barely, but
Yeah, that was on me entirely. I've done this class 5 years in a row. I thought the test was good. There were there were two questions that had errors on them. And basically what I've decided to do is I'm going to give you a second chance at answering the questions.
Okay, thank you.
Well, no, it's not a thank you thing. The only other option I have was to just drop them all together. And literally speaking, for the one question, I didn't think you wanted me to do it. Okay, let's get in here. I don't even know if I'll be able to access it now because it may not be available to me. Okay. Okay. This thing. Okay, you're in here, right? Does this look familiar to you?
Yes.
Mm-hmm.
Nope, that's the wrong thing. Crap. That's not where. I don't need to be in discussions. I want to be in the report sheet. Ugh. This is what's frustrating about this. Okay, let's go to modules. Okay, let's try another one then. Now that one you did online. Okay. Are you seeing, you're normally coming up to this and seeing this screen, correct?
Yeah.
Yeah.
Hi, Jennifer. All right, you're hitting start assignment, right?
Mhm.
Mm-hmm.
All right. How are you uploading the files?
I'm just clicking upload file, and then I have them saved on my computer.
And then choose file. Basically,
File.
what you're doing is you're taking a picture of the thing, storing it somehow on your computer, and then accessing it. Is that correct?
Yes.
Jordan?
Yeah, I print out the worksheet and handwrite everything
Mhm.
and then take a picture
Okay.
and email it to myself and then put it in a Word document and then upload
So
it
you're
that way.
putting it into a Word document, but in any case, both of you are, you're storing it in a file and then you're accessing the file, correct?
Yeah.
Mhm.
You're not downloading anything.
No.
All right, thank you. I needed that because I've got two people that are downloading it into this. Somehow they're downloading it in there. And when they download it, it takes forever for the files to pop up. So another thing, guys, why didn't any of you submit your graphs? The heat of vaporization lab. You had
I
to make a
submitted one.
graph.
I
If you see
submitted
the,
a graph.
go ahead.
I went back and forth about submitting a graph, but I didn't see anything on the like lab sheet that said we had to, so I just didn't submit
I think
one.
it said
But
draw a graph, Jordan.
Oh.
Okay.
I actually submitted a graph. It was the last page with the same PDF that I sent. I don't know if
Did you get your grade yet, Jennifer?
I don't know if you altered it. I haven't checked.
If I altered it. Okay. Let's see.
I submitted a graph.
Okay.
It was, I had like the chem.
Okay, it's not a big deal. If the thing says to draw a graph, stop. I said leave student view. Why are you not leaving student view? Stop share screen.
It was just on a different file for me.
Why is this? Thank you. I'm sorry. I haven't finished grading them yet, so. I don't want. Why do computers do what you tell them to do rather than what you want them to do? All right, heat of vaporization. Oh, where's it at now? There we go. Okay. Worksheet. It says graph. Okay. Guys, if it says graph, or if you need the graph to do information, include it from now on, okay?
Mhm.
I will give those 10 points back. But from now on, if it says anything about graphing, make sure that you do that, all right?
Okay.
Is that fair enough?
Yes. Yeah. So was it supposed to be like a hand-drawn graph on the worksheet, or was it supposed to be
No,
like an Excel
you
graph?
got an Excel. Do you know how
Okay.
to Excel graph? You
No, yes,
should.
I have it. I have it. I think I didn't put it in the same document as my lab. I had to download one document and then download the screenshot of my Excel graph. So it wasn't on the original document.
Don't worry about doing it now.
Okay, no worries.
Just from now on, if it says anything about graphing, then include the graph. Okay?
I'll put it on the same document then.
Yeah. Well, whatever you have to do. Okay.
Mhm.
Fair enough. Okay, I've got you three in. All right. Jenna, Jordan, and Jennifer. Okay, guys, did you have any questions about the last laboratory before we go on from here? The last laboratory was the kinetics lab. Or have you not done it yet?
I did it, but I'm good.
Okay, Jenna.
I did the pre-lab and then I watched your simulation video, so I was gonna do it this afternoon, but I understood everything in the simulation video.
It's not as bad as the last one. Okay, it really isn't as bad. Just work your way through it. The general gist of what I get is if you work your way through it, you can get a fairly good grade because it doesn't allow you to submit wrong answers. Okay, Jennifer? Jennifer, you just gave me a little
Yeah.
nose nudge.
I just need to do the post lab for that assignment. I got the general concept of it.
Okay, so everybody's good on that? It was basically the same. No, actually it wasn't. I'm sorry. My mind's going back and forth between the face-to-face and this lab. Basically, all you had to do was basically just compare the temperature with the regular lab. Concentration was the first part and temperature was the second. Okay. In a way, it's unfortunate that you're dealing with this before the lab lecture because you haven't had equilibrium yet. Okay. So we're going to have to go through a little bit of that first, and then we're going to get into the gist of the lab. It's really, really not that difficult. It's not like manipulating equations that we're going to have to do at the end of this chapter and continuing on into acid-base reactions, which is the next chapter. So we're going to get through this as best we can, and make sure you get to the lecture this afternoon. Okay. Are you seeing the slideshow?
Yes.
Okay. Man, I am having a bitch of a time today. There we go. I just had my computer worked on and it's a bit wonky. All right, guys, what you have to understand is that when you see a chemical reaction, you need to realize that it's not 100% going from reactants to products. Sometimes what happens is the products get together and they react with themselves to remake the reactants. And so you have this process going, things going forward, reactants to products, and then the products going back to reactants. Well, if that occurs, what happens is you get something called equilibrium, where eventually you get the rate of the reactants going to the products being the same as the products going to the reactants. Is this kind of making sense to you? So if the rates are equal, then the concentration of each one of my stuff is not changing because the rate I'm making FeSCN2 plus is the same rate that I'm depleting it. So the concentrations aren't changing anything. So I can literally take the concentration of all my stuff, putting my products over the concentration of my reactants. And what's going to happen is I'm going to get a constant. Again, does this make sense to you? I'll do it. I'm going to go through a larger explanation in the lecture today, but this ultimately is what is happening. We have to understand that if I have a reaction that's in equilibrium, I can take the concentration of the products and divide that by the concentration of my reactants, and I will get a constant. The other thing you have to realize is if I do have coefficients in front of these compounds, then that concentration gets raised to that power. So if there's a 3 in front of the FeSCN2 plus, then the concentration gets raised to the third power. Are we good? Who's on the iPhone? Shari, are you on the iPhone?
It's me,
Shari?
Benita.
I'm sorry?
Benita.
Sorry, Benita. Okay.
It's okay.
So are we good with this part? Benita, you're the first non-J person I have in here today. Are we good with
That's
this?
good.
We good with this slide? All right. Now, another thing is, and I'll go over this later on, it's an easy abbreviation. If I want to write concentration, I just put brackets around the substance that I'm taking the concentration of. So if I want to redo my chem equilibrium, you will see them as this expression at the bottom. So basically, if I can find the concentration of each one of the things in the reaction, I can determine the equilibrium constant. And that's basically where we're going with this. Now, in order to do that, we have to have a way of observing the concentrations. The way we're doing it in this lab is something called Beer's law. Some substances, like human beings, absorb ultraviolet rays, sometimes much to their detriment. And the amount of ultraviolet light that's absorbed is directly related to the type of substance it is. It's related to how much of the sample the light sees, and it is related to the concentration of the substance. First number today is 19. Again, this is not for your benefit. This is the benefit so I know that people are viewing the video. First number is 19. Okay. The reason, I'll get into the reason in a second. Basically, we can relate absorption to concentration by taking in each one of these factors. Beer's law states that the absorption is equal to the molar absorptivity of the compound, which is a constant that is related to each individual compound. B is the cell length, and C is the concentration. If we're looking at colors, we have two colors here. They have different dyes in them. They're both blue, but they're different colors of blue. So the amount of the light that gets absorbed, remember, what we see is what light gets reflected. These two shirts are actually absorbing red light, reflecting blue. That's why we see them as blue. Now, the sky blue is absorbing light. The dye in the sky blue shirt is absorbing light at a different amount as compared to the royal blue shirt. So therefore, the dye in the sky blue is actually absorbing more than the royal blue shirt is. Royal blue is reflecting more. So that's an example of how the type of substance deals with the amount of absorption. Now, if we look at concentration, the left vial here is less concentrated than the right one. As light is going through here, and it's going through a straight path, the light going through the left vial is going to see less of the molecules than the one going through the right. So the one on the right here is actually absorbing more light because it's more concentrated. Similarly, if I double the path length, I'm seeing twice as many molecules if I double the path length. So doubling the path length is going to mean that I get more of the light absorbed. That's why the absorption depends on the type of substance, the path length, and the concentration. Now, we're able to get rid of one of these things by saying, okay, each time I put something into my instrument, I'm going to dictate that the cell length is going to be 1 centimeter. If I do that, then that's going to get absorbed by the molar absorptivity. And I've now changed my expression to the absorption is equal to my molar absorptivity times my concentration. If you think of the y-intercept being 0, Again, like I've said all along, what we're trying to do here is we're trying to develop a graph, a straight line graph, so that we can measure two things and use the slope of that straight line to determine a third. We can't directly measure molar absorptivity. So what we do is we create a series of solutions of varying concentrations. Then we put them into the instrument. We measure the absorption versus that concentration. We get a graph. That graph has a straight line. The slope of that graph is then going to be our molar absorptivity. And I've just explained that. Any questions so far, ladies and gentlemen? So what we're going to do is we're going to make a graph like that. Or actually, you're going to make a graph like that, and we are going to submit it. Everybody shake your head. Everybody's going to submit it this week, right? So you're going to make a graph of absorption versus concentration, and you're going to get a straight line. The straight line slope is going to be equal to the molar absorptivity. That's the whole reason we're doing the first part of this experiment.
I have a question.
Crap.
Wait, can you hear me?
Yes, I can hear you.
Is it made on Excel or do we do a handwritten graph?
Please do it on Excel. If you know how to do it on Excel, please do it on Excel. All right.
Okay, thanks.
Do you need to see the graph, guys? Because if you do, I'll be perfectly honest with you. I got done. I got done with your PowerPoint, and I used your PowerPoint to do the face-to-face labs PowerPoint. And what happened was I happened to save their PowerPoint over your original one. So I had to redo it. And when I redid it, I lost the graph. Do you need to see the graph? Jordan, Jennifer, Benita, does anybody need to see the graph of the absorption versus the concentration?
I don't think so.
Anyway, that's what this slide was supposed to be. All right. Now, I can't believe this. Hold on a second, guys. Something wonky is going on with my something wonky is going on with this. And you're going to have to bear with me for a second, guys. I'm sorry. Ah, damn it. And this may be something, just bear with me for a second, guys. I'm sorry. It has a lot to do with the fact that there are the same course, but two different curriculums are taught with it. Okay. Okay. Again, I apologize, ladies and gentlemen. All right. Okay. So it turns out I did. All right. I do have the graph. All right. So basically, you're doing absorption versus concentration, and you're going to get a straight line. You're going to get a equation of that line, and the slope is going to be equal to the molar absorptivity. Are you with me, guys? All right. So the strategy we're going to do, we're going to create standard solutions, and we're going to obtain the absorptions from those standard solutions. Then we're going to graph it as absorption versus concentration. That's going to give us our molar absorptivity. Our molar absorptivity, because of Beer's law, absorption is equal to molar absorptivity times the concentration. If I have an unknown solution and I know what the molar absorptivity is, I could take the absorption of that unknown solution, divide it by the molar absorptivity, and I'm going to get the concentration. Does that make sense to you? So that is basically what we are going to do. We're going to do that. What that's going to do is that's going to give us our concentration of our iron thiocyanate. We're going to use that concentration and the initial concentrations of our Fe and our SCN to get their equilibrium concentrations. So the only thing in our reaction that's absorbing ultraviolet light is the Fe-SCN. Originally, when I mix these two things together, I have no Fe-SCN. And as I mix them, what happens is the Fe and the SCN react together to make some Fe-SCN. And eventually the Fe-SCN starts to go back and make the Fe and SCN. So we got this cyclic process. and we have the rate going towards FeSCN equal to the rate going towards the Fe and the SCN. So what I'm going to do is I am going to get the initial concentrations of my Fe and my SCN. And then I'm going to figure out how many moles I have. The concentrations you're given originally are 2 times 10 to the minus second molar. These numbers are fudged, guys. Use the numbers that you actually have in your charts. So if I have my molarity and I multiply it by my liters, that's going to give me my moles of iron initially. If I have my original concentration of SCN, multiply that by my liters, I will get the moles of SCN initially. I do that math out. I multiply my 5 times 2 times 10 to the minus second molar times 1 over 1,000. I get 1 times e to the minus 4th moles of Fe 3 plus. Do the same thing for my SCN. I get 2 e to the minus 5th moles of FeSCN. Now, remember, we're mixing these solutions together. And we're taking those test tubes that we make and we're putting that into an ultraviolet spectrophotometer. We're going to put it in there and we're going to get the absorption. We've already plotted absorption versus known concentrations, so we know what the molar absorptivity is. All we're going to need to do is take our absorption, divide it by our molar absorptivity, and that's going to give us our concentration. Now, the thing about this is we have to realize what the total volume of our solution is. We've added 5 milliliters of our iron solution, 1 of our thiocyanate, and 4 waters. The reason we're doing it this way is we are trying to keep the concentration of our FeSCN the same. If we don't add water to this and keep the total volume between SCN and water constant, then the concentration of my iron is going to change. So we have a total of 10 milliliters of our reaction solution. So I'm going to take my concentration of my FeSCN, multiply that by the milliliters and liters. That's going to give me my moles of my FeSCN. Now, where did these come from? Where did the moles of FeSCN come from, Jenna? Caught in mid-yawn. Where'd they come from?
Yeah, from the original part, right?
They came from the FeSCN, came from the Fe plus 3, and it came from the SCN. So if I made some of the FeSCN, didn't I take it away from the Fe? And didn't I take it away from the SCN?
Yeah.
So I'm going to use that. I've got the moles of FeSCN, plug them in there, and I'm going to use that fact that the moles of the FeSCN came from the moles of Fe. Now, it's a 1-to-1 molar relationship. So I don't have to involve any molar ratio. The moles of FeSCN I can subtract directly from the moles of Fe. That's going to give me my moles of Fe at equilibrium. I then have to divide that by the total volume, which is 10 milliliters, in order to get the concentration of Fe in the reaction mixture. I'm going to do the same thing for the SCN. I'm going to take the moles of SCN initially, I'm going to subtract out the moles of FeSCN. This gives me the moles of SCN minus at equilibrium. Again, I divide that by the total volume of the solution. I have the concentration of the SCN. I now have all three equilibrium concentrations. I've got the Fe, I got the SCN, and I have the FeSCN because I directly measured that with the absorption. I'm going to plug those three numbers into my expression, my K equilibrium expression, and I'm going to come up with a constant. Now, guys, there is no rule of thumb for K equilibrium. It can be a very high number. It can be a very low number. So whatever you get is whatever you get. Since the only thing that's going to change the K equilibrium is going to be temperature, all of your K equilibriums that you calculate should be the same. So you need to give me a standard deviation for this experiment. Are you familiar with how to do a standard deviation? Jordan? Jennifer? Benita? Does anybody need refreshing?
Yes, please.
Okay, I'll make a new slide. Home, new slide. Okay, you only do this when all of your answers should be coming out to be the same thing. So standard deviation. The first thing you need to average the trials. Then my standard deviation is going to be equal to the trial 1 value minus the average. I'm going to take the absolute value of that. To that, I'm going to add the absolute value of trial 2 minus the average. To that, I'm going to add the absolute value of trial 3 minus the average. I'm going to continue this on until I get to, you guys seem smart enough to understand this, my last trial. So I'm going to call my last trial, trial N minus the average. And I'm going to divide it by the number of trials. So what's going to happen is I'm going to have my average value. All right, we're going to do some numbers. I have 6. Give me a number, Jenna. Give me a
8.
number. Jordan, give me a number.
2.
Jennifer?
12.
And Benita? Benita?
Professor T, I'm at a doctor's office, but 5, and I can't talk right now.
Okay.
Okay.
And for kicks and giggles, we'll do that. Okay, I'm going to add these numbers. My average of the numbers is equal to amazingly enough, my average is 8. Okay, so to get my standard deviation, I'm going to take absolute value of 6 minus 8 plus absolute value of 8 minus 8 plus 12 minus 8 plus 5 minus 8 plus 9 minus 8. I've got 5 trials, so I'm going to divide it by 5. So I get 2 plus 0 plus 4 for 6 plus 3 for 9 plus 1 for 10. So I get 10 divided by 5, which is going to be equal to 2. So what this really means is that my value is 8 plus or minus 2. So I have a range. My value really can be anywhere from 6 to 10. Does that make sense to you guys? It's a measure of how precise your measurements were. Anybody have any questions about what we're doing here today? Jordan, scratching your head or a question?
Just scratching my head.
Probably the best thing you've done this last half an hour or so.
I had a quick question about the quiz.
The
if
quiz.
that's okay.
Which quiz?
The
Lecture quiz?
Yeah.
Okay.
I just wasn't sure. There was a question about like equilibrium constants,
Mm-hmm.
and I like read the book and I'm just a little confused if it's like they're unitless or it's moles per liter. Like I'm just kind of
It
confused.
changes.
Okay. It
It
changes.
changes. Okay. All right. Are you seeing this expression that's right here?
Mm-hmm.
All right. I've got right now, there's nothing, no exponents on this. So I literally have moles per liter divided by moles per liter divided by moles per liter, right?
Mm-hmm.
So literally the label of my KC is moles per liter to the minus 1.
Okay.
If this reacted with this to make 2 FESCNs,
Mm-hmm.
then my exponent on my FESCN would be a 2. In which case
Okay.
I would have moles squared per liter squared over moles per liter times moles per liter. So it would be unitless.
Got
So
it.
it depends upon what the equilibrium expression is, Jenna, what the
Mhm.
label could be.
Okay. Thank you.
Okay, I just want to make sure I am in, right now, I am in your class. The thing that makes it confusing is the face-to-face is doing this whole experiment by a different method. This looks like yours, and you've got these, you're going to use this table to do your graph with. Then you've got these solutions. These are what you have done. The first trial, you've added 5 milliliters of the iron nitrate, 1 milliliter of the SCN, 4 milliliters of water. All the total volumes are going to add up to be 10. Then you're going to have to go to the survey. The survey is there. And hopefully the survey will hit the preview. Now you have your 5 absorbances. This data,
We can't see anything, or at least
oh, I'm sorry. I apologize. Well, you can't see this at all?
I just see the PowerPoint, or now I see you.
Okay. All right. I'll show you how to get back to there again, okay? I may have to do this. I may have to reshare the screen for each particular. It may not be able to flip with me. Sometimes that happens in Zoom. All right. You are going to the equilibrium constant determination. It gives you a little bit of introduction. It gives you the calibration curve. It gives you the pre-lab. And this first table, the first table that you have is, you have different concentrations and the absorbances of those concentrations. You're going to use this to make your graph. Again, please include the graph. Second thing, you're going to go down here. You can watch them do the video. It's of minimal use. You're then going to go to survey. Are you seeing where where it says survey? Are you seeing the equilibrium constant data? You may not be able to see the next screen. You're going to go down here. You're going to hit preview. And you are going to get a series of these solution numbers correspond to the individual trials you have. And you've got 5 different absorbances associated with those. That's where you get your absorbance data. You're going to take this number, divide it by the slope of your graph. That's going to give you your FeSCN concentration at equilibrium. You're going to then multiply that concentration by 10 milliliters times 1 liter over 1,000 milliliters. That will give you the moles of FeSCN2 plus at equilibrium. You're going to use the information in data table 2. It gives you the concentration and the volume of the Fe and of the SCN. You're going to use that information to get the moles of the Fe initially and the moles of the SCN initially. From the Fe initial moles, you're going to subtract out the moles of FeSCN. That will give you your moles of Fe at equilibrium. Divide that by 10 milliliters made into liters. You're going to do the same thing with the SCN. You're going to take the SCN initial moles, subtract out the moles of FeSCN at equilibrium. You do this subtraction, that gives you the moles of SCN at equilibrium. Divide that by 10 milliliters made into liters, and you will have the concentration. You now have the 3 concentrations. Take the FeSCN concentration, divide it by the Fe concentration multiplied by the SCN. Any confusion, guys?
I just want to make sure of something.
I'm here.
So for step 2, you would divide the absorptions that we got from the reading divided by the slope of the graph that we would get from plotting it.
Yes. These absorptions, Jennifer, that you got from going into the survey and hitting the preview, these absorptions, you're going to take this absorption, divide it by the slope.
Okay.
It's going to be a small, relatively small number. Okay? It is going to be a relatively small number. Like on the order of like maybe up to 10 to the minus 7th. Second number is 75. First number was 19, second number was 75. You don't have to do it. Jenna, if you're writing that down, you don't have to do it. You were here. I've got you marked as being present. If you guys don't have anything else, then
I do have a quick question, but it doesn't really like pertain to like the numbers in the lab.
okay.
How long does it take the recording to upload into Canvas?
The recording from this lecture,
Yes.
sometimes more, sometimes less.
Okay.
It's definitely beyond a day, Jordan.
Okay.
And the reason that is literally speaking, I have this meeting from 8 until sometimes, guys, we've been here for an hour and a half. At that time, I got to take a quick shower. I then have to teach my lecture, which goes until 12:20. Then I drive out to HCC, teach a lab for 2.5 hours, drive back here. Generally speaking, guys, if it's that intense, my mind is fried at 5 o'clock. So I don't do any work then. I probably will do work today because I have to devote tomorrow specifically to grading tests. Any other questions? Benita, I do appreciate your being at work and doing this. I do appreciate
Thanks.
that. There are other people that are at work and decided to blow this off. And really and truly, guys, I do appreciate you all coming here because literally speaking, I can look directly at the grades, especially for the heat of vaporization lab. And those people that didn't attend did not do very well on it. Jordan, I think you need practice on doing logs. If I
Okay.
remember correctly.
Okay.
Some of your calculations were off because of it.
Okay.
If that's it, guys.
Wait, hold on. Quick question. Sorry. So for the test, like, are we gonna have like a Zoom, like to kind of go over it and stuff, to go over some of the questions?
Benita, yes, we will. We will have time to go over it. I am going to wait until Tuesday because as I explained in my email, there were distinct problems with 2 of the questions. On the heating curve one, I didn't give you a weight of water, and on the one in which I wanted you to determine the order, there was a typo on it.
Oh, okay. Okay.
And luckily one of your fellow students, basically what you should have seen was that it went from 0.2 to 0.5 and then down to 0.1. What you should have seen is a gradual decrease in the concentration because we're monitoring something that was a reactant. And it was my fault for not seeing the typo. But a lot of times when you're doing a test, you just become you know what the answer is and you know what you have to do. So you're not seeing the little errors like that. I apologize. It should not have happened and it will not happen for the next 3 tests.
Okay, that's fine.
I just didn't have time to go through. I didn't have time to go through and do the test before I gave it to you guys. And for that, I really apologize. So be aware that there's going to be, I'm going to send out an email. There will be a practice test, and the practice test will have on it these 2 questions that you're going to have to do over again. Okay.
Mm-hmm.
And yes, Benita, remind me on Tuesday,
Okay.
and we will go over the test if you so desire.
Okay, perfect.
How were they thinking questions, guys? The multiple
challenge-
choice ones.
They were quite challenging for me. I don't know about anybody else.
I'm sure they were. That's why, literally speaking, Benita, the reason I make them challenging is when you take that MCAT test, you're going to have a lot of those same logic questions. When the American Chemical Society gives their test, it's called the Olympiad or something like that. When they give their test, they give you 70 questions in 60 minutes. They don't expect you to finish the test. But a lot of times what you're supposed to do is questions like, I gave them the thinking questions, which you're supposed to look logically and say, oh, I know for a fact that this is the reason, so I can answer the question like that. Call me right or wrong, Benita. That's the reason I do it.
Right. Okay.
Any other questions, ladies? I can't even say gentlemen because there's nobody here. Okay, take care, guys. By the way, don't pay attention to the email I send out saying that you need to put the graphs in. You've already got that information. Jennifer, Benita, take care. I will see you later, or I will see you on Tuesday.
Okay.
Okay, bye.
Bye.